Hi everyone, welcome to this lecture. So in this lecture, we will learn how to perform backward propagation and how to write the equations for the backward propagation. So in the previous lecture, we learned about the forward propagation. So in forward propagation, we move from input layer towards the output layer, and we form the equation both for the neurons of the hidden layers and also for the neurons of the output layer. Now in back propagation, we will move in the backward direction, that is from output to the hidden layer and then from hidden to the input layer. And during this movement or during this propagation, we will also form the equations. So in the forward direction or in the forward propagation, we learn how to get the equation of OK. So basically, OK is the output of the neural network. It is also the predicted value of the neural network. So OK is the predicted value and TK is the actual value. So the difference between the targeted value, this TK is the targeted value and OK is the predicted value. So if we find the difference between TK and OK, we will get the error. So that error is obtained during the forward propagation. So during the backward propagation, the error is propagated back through the layers of neural network, and then we update the weights of a neural network so that we can get the improved performance from the neural network. So in the forward direction, we calculate the error. And in the backward direction or in backward propagation, we reduce the error with the help of weight. That is, we update the error, so we update the weights so that the error can be reduced or the performance of a neural network could be improved. So in the first step of a back propagation, we will move from output K to hidden J. So this is our output K and this is our hidden J. So now we are starting the backward propagation or a back propagation, and we will move in the first step from the output K to the hidden J. Okay. In that movement, we will write the gradient equations or the differentiation based equation for the back propagation, and we will update this weight. So basically, if we move in the backward direction from output layer to the hidden layer, it means we have to update the weight between the output layer and the hidden layer, and that weight is WKJ. So basically, we have to reduce the weight, we have to reduce the error with the help of this weight. Therefore, we have to write the equation dE by dWkj, that is rate of change of error with respect to weight Wkj. Since we are moving from output to the hidden, therefore we have to update the weight that is present between the output and the hidden layer. And while updating the weight, we will reduce the error. So now we have to learn how to reduce the error with the help of the weight between the output layer and the hidden layer. Therefore, we need to learn how to write the equation of rate of change of error with respect to WKJ. So this is our neural network. This is the output of the neural network. And we know that after the output of the neural network, which is the prediction of the neural network, we calculate the error by subtracting this predicted value from the actual or the targeted value. So error is somewhere here. So usually we do not show error in neural network. So we know that error is somewhere here after the output of the neural network. So we will start from error. So from error, we will reach to OK. Then from OK, we will reach to net K. And from net K, we will reach to WKJ. So we have three steps. Starting from the error, we will reach to WKJ. This WKJ is our parameter, which we have to update in order to reduce the error. So in that case, if you see the equation, it has three terms. Why three terms? Because from error to WKJ, we have three steps. From error to OK, then from OK to net K, then from net K to WKJ. So the equation will be dE by dOK. That is, first we will find the rate of change of error with respect to OK. Then we will find the rate of change of OK with respect to net K, and then net K with respect to WKJ. So if we move from error to WKJ, we need three steps. And for every step, we will write the gradient equation. So here we are using a gradient in the back propagation, and we have three terms when we are moving from the output layer to the hidden layer. Now, the first two terms are called the error signal between the layer K and J. So these two terms may be denoted by a delta k. So we will denote them by delta k, but first we have to find basically these three values. So here we have just written the equation for the back propagation when we move from the output layer to the hidden layer. We see that we need 3 steps in order to reach from the error to WKJ. In that case, we have 3 terms having the gradients. Now we have to find the value of this term, we have to find the value of this term, and we have to find the value of this term. Now we need to find 3 values, and after finding these 3 values, we will put those values here so that we can get the exact value of this gradient, that is rate of change of error with respect to WKJ. Let's start by finding the value of dE by dOk, or rate of change of error with respect to OK. So I need to find this value dE by dOk. Now, what is error? So we know that error is the difference between the targeted value and the predicted value. So this is our error. So here we need to take the first derivative of the error. So with this simple equation, we cannot take the derivative easily. Therefore, we have transformed this error into the square error. So here I am squaring the error, and then I am using half. This half is only for mathematical convenience. Now, what is the mathematical convenience? So mathematical convenience is here when we take the derivative of this E with respect to OK, we can see that this is the derivative. So this is basically like x square. If you treat this whole bracket as x, so this is x raised to power 2, that is x square. So we know that the derivative of x square is 2x, 2 times of x. If we have x square, so its derivative is 2x. Similarly, if we have tk minus ok raised to power 2, we have a derivative 2 times of tk minus ok. So what will happen? We use this half for our mathematical convenience, that when we take a derivative, this 2 will come at the start and this 2 will cancel with this half. In that way, we will get a simplified form of equation. So that was our error. Here we transform the error into the square error. Then we add half. It will become half tk minus ok square. So this is our error to which we have to differentiate it. So this is dE by dOk. Here I am taking the first derivative of this error. So 2 tk minus ok, then according to the chain rule, we have to find the derivative of this bracket as well. Since we are differentiating or taking the derivative with respect to OK, therefore the derivative of tk is 0 and the derivative of OK is 1. So if I take the derivative according to chain rule, if I take the derivative of this bracket, it will be 0 minus 1. So 0 minus 1 will be minus 1 only. So this is the derivative of this term, and according to chain rule, the derivative of the term inside the bracket is minus 1. Now this 2 will cancel out. This minus 1 will come at the start and we will left with tk minus ok. So in this way, we have found the value of rate of change of error with respect to OK. So we have calculated the first term in our equation. Now it's time to calculate this second term. Now we know that from the forward propagation, we know that OK is the activation function of net k. So if we use activation function as a sigmoid, then based on the sigmoid equation, this is the equation of OK. So we have OK. Now we have to take the derivative of OK with respect to net k. And we see that inside OK, we have a variable called net k. Now we can easily differentiate this OK equation with respect to net k. So here we are differentiating OK with respect to net k. So the next step will be that we see that in the denominator, we have 1 plus e raised to power minus net k. So we will move this denominator to the numerator so that we can differentiate it. So if we move this whole term to the numerator, it will get minus 1 as a power. So we can see that here we have moved the whole denominator to the numerator. So its power become minus 1. Now it's time to take the first derivative of this term. So according to rule, this minus 1 or any power, if you remember, if it would be x square, then 2 will come at the start. So it is not x square. it is something raised to power -1. So -1 will come here. Then we have the term. Then we have to subtract -1 from the power. It will become -2. This is all according to the concept of a differentiation. Then according to chain rule, we have to take the derivative of this bracket. So the derivative of 1 is 0, and the derivative of exponent term is always the same as an exponent term. Then according to rule, we have to take the derivative of the power of the exponent. So since we are taking the derivative with respect to net k, therefore the derivative of minus net k will be -1. So in this way, this step shows the first derivative of this term, that is 1 plus e raised to power minus net k to the power -1. Now let's simplify it. This -1 and this minus will become plus. Then this 0 plus exponent term, we will only get the exponent term. And this term has raised to power -2. Now I can move it to the denominator, so it will become +2. So after simplification, this term will become this term. Now what we can do, we can see that we have a square here. Since we have a square here, therefore we can split it into two terms. So this is the first term and this is the second term. And here we have add 1, because we know that if we multiply something by 1, it will not change its value. Okay, now what is this? If we see, this is 1 over 1 plus e raised to power minus net k. This term is okay. If we go back, we can see this term is okay. Now, after taking the derivative of this, we can see that this term becomes okay. Now, what we did here with this term, now we are left with this term. So we add +1 to this term, and then we add -1 to this term. So this term become okay, and to this term, we add +1 and -1 in order to balance, because we know that we cannot add +1 without any reason. So if we need +1, so in order to balance it, we have to add -1 as well. So this is okay, and here we have add +1 and -1. Let's see what we are going to do in the next step. So basically in the next step, we are going to break the LCM. How to break the LCM? This denominator is written both under this term and this term. Let's see what we are going to do. So here we are breaking the LCM. If you see, I am breaking this term separate and this -1 separate. So I am separating this term, and I am writing denominator under each term. Now what will happen? This will cancel out and I will get 1. And again, if we see this term, it is again okay. So this is the simplification of the term, that if we take the derivative of okay with respect to net k, we will get okay 1 minus okay. So that is our okay. If we see, we started from here. That was our okay. Then we take the first derivative of okay with respect to net k. In order to take the derivative, we move this denominator term to the numerator term. Here we get this form. Then we take the first derivative, this -1 come here, and then we subtract -1 from the power. It will become -2 according to the rule of differentiation. Then according to chain rule, we calculate the derivative of this term, which come out to be this. Then we calculate the derivative of minus net k, which was -1. That -1 and -1 will become plus, and by rearranging, we will get this term. Then we split this square into two terms, that is 1 plus e raised to power net k and 1 plus e raised to power net k. Then we replace this term by okay, and then we add +1, and then we subtract -1. Then we break the LCM. So here we are breaking the LCM. This term becomes 1 and this term becomes okay. Now that was the calculation of a second term that was present in our backpropagation equation. Let's move to the third term. Now the third term is, we have to find rate of change of net k with respect to wkj. Now where is net k? We basically need net k, equation of net k, in order to take the derivative. We know that this equation net k, which we calculated in the previous lecture, where we learn how to write the equation during the forward propagation. So that was the equation of net k. Now here I will put the equation of net k, and here I am taking the derivative. Since the derivative is with respect to kj, therefore the derivative of bk with respect to kj becomes 0. And the derivative of wkj with respect to kj becomes 1. So we are left with only oj. So the derivative of this term will come out to be oj. Now we have calculated all these terms. Now it's time to put the values back. So if you remember, that was the equation of a back propagation in moving from the output layer to the hidden layer. And now we have calculated the values of each term present in this equation. Now it's time to put the values. So we know that the value of this term is minus tk minus ok. The value of the second term was ok, 1 minus ok. And we have just calculated the value of third term, which is oj. So if we put all these values, we will get the equation like this. And we know that this is our error signal, that is delta k. If we replace these terms by our error signal delta k, we will get this. So finally, we have successfully calculated the rate of change of error with respect to wkj. So this is the gradient of error. Now we have to use this value in order to update the wkj. So here is the updation of WKJ. So how to update WKJ? So updated value of the WKJ will be called as WKJ new. That will be the old value. So in order to update the old value, we have to add this term, that is the gradient of error. And we have to associate a learning rate. So here eta, this symbol which is eta, it is known as learning rate. Now it's time to put the values. So this is eta, and we have just calculated this in the previous slide. It is minus delta k oj. So put here minus delta k oj. So plus minus becomes minus, and this will our value of the update. So that is our old weight, and that is our new weight, which is updated by this value. So in this lecture, we learn that during the back propagation, first we move from the output layer to the hidden layer, and then we move from the hidden layer to the input layer. So in this particular lecture, we only move in the backward direction from the output layer to the hidden layer. First, we write the equation of a back propagation. We saw that there are 3 derivative terms in the equation of a back propagation. Then we calculate the values of all these 3 terms. We basically derive the values of all these terms. Then we put those values in that equation, and then we simplify. After simplification, we get the value which is minus delta k oj, and that value will update wkj. So we will use this value in weight updation along with the learning rate. So this is the updated weight of wkj. So in this lecture, we learn how to update the weight using back propagation if we move from the output layer to the hidden layer. So in the next lecture, we will move from the hidden layer to the input layer. That is the second step of the back propagation. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture.